Okay, so we are looking at how to start analyzing how people choose different bundles of goods to buy. So we're going to be looking at situations here where we can acquire two different goods. So in these examples, there's only two different possible goods in the entire world. The first one we're going to look at is we're going to assume we are shipwrecked on an island. We have 24 hours in a day, and we can use that time to either go fishing or to try to harvest coconuts. So for each hour of fishing, we are going to catch half a pound of fish. For each hour spent harvesting coconuts, we harvest 1.5 pounds. So what we want to do is come up with a graph that shows all the different combinations of fish and coconuts that we could produce in a day, or we could afford to get with our time. So we're going to start with imagining a situation where I spend all 24 hours fishing. So if I have 24 hours in a day and I catch 0.5 pounds of fish per hour, I'm going to end up with 12 pounds of fish. So fish, we put that on the vertical axis. So if we spent all of our time only fishing, we would end up with 12 pounds of fish and no pounds of coconuts. If I spend all of my time harvesting coconuts, it'd be 24 hours in a day, 1.5 pounds of coconuts per hour, I would get 36 pounds of coconuts. So that's going to be right around 32, 34, right around here. So if I spent all day harvesting coconuts, I'd have 36 pounds of coconuts and no pounds of fish. And then to see graphically what all the different possible combinations of fish and coconuts are, we just draw a straight line connecting the two intercepts. So in 24 hours, we could produce any combination of fish and coconuts along this line. So what would be good for you all to do right now is to pause and try to confirm that the point where you spend 12 hours harvesting fish and 12 hours harvesting coconuts is also on this line. Well, that's fascinating. Okay, so here's a graph with the line drawn in on it. So first of all, I want to talk about a couple things. This kind of graph is called a budget constraint. It's going to be super important. But come on, pen. Okay. Anyway, maybe the pen will come back. So this is called a budget constraint. It shows all the different points that we can afford. So let's talk, first of all, why we only care about the first quadrant. In this course, we're not going to consider the situation where we're producing negative amounts of goods. So in a situation where the two axes are the amount of goods that you are producing, or the amount of goods you can afford, we only care about positive quantities. So we're going to be focused on the first quadrant. Also, let's talk about what the slope means. So the slope represents, I think the pen's back. The slope represents how quickly we can trade off one good for the other. So if I give up an hour of my time, how much fish do I give up and how much coconut do I get in return? So in this world that we're looking at right now, the budget constraint is linear because the amount of coconut I gain per hour of time I give up fishing is constant. And we're going to look on the next slide whether or not that's realistic. But the rate of trading off between fish and coconuts is constant on this island. So that's why the budget constraint is linear. The next question here is, would we ever end up consuming a combination of fish and coconuts below the budget constraint? So would we ever choose a combination of fish and coconuts right here? So this would be like 6 pounds of coconuts and 7 pounds of fish. And the answer is no. Any of the bundles that are inside and here, we're not using all 24 hours to produce goods in those situations. I can get to this point using less than 24 hours in the day. And in all the examples we're going to look at, we are always going to assume that consuming more is better. So I would never choose this point. In this situation, we are ignoring the need for sleep and other activities, and we're just assuming that you could spend all 24 hours a day doing these two activities. Doesn't seem like maybe you'd have time to eat any of the stuff you're harvesting, but whatever. So the answer is no, we would never end up at any point that's underneath the budget line, and we could also never end up at a point that's above it. To get to this point here, I would need more than 24 hours in a day to get to that point, and we can't get there. So a lot of times you'll hear all the points that are under the line called the feasible set. We can feasibly get to all of those different combinations of goods. And out here above the budget constraint, you'll hear this is not feasible. We can't reach any of these points because there's not enough hours in the day. Okay, let's look at another example of a budget constraint. This one's not going to be linear. We're going to talk a little bit about what that means. Okay, so here we have a budget constraint. Again, let's assume that this is fish and coconuts. So fish and coconuts. So what this means is that in this world, on this island, the trade-off between fish and coconuts is not constant. And let's talk a little bit about why that might make sense. I think the example of coconuts is easier one to think about. So if you think about actually harvesting coconuts, you're going to have low-hanging coconuts and then coconuts that are way up at the top of the tree. So when you first start your day and you start going to harvest coconuts, you are going to get the low-hanging coconuts first. So in your first hour of harvesting coconuts, you might harvest a lot of coconuts. It might be really easy to get all the low-hanging ones. But then as you harvest all of those, eventually you're going to have to try to start harvesting the coconuts that are in harder to reach places. So in fact, what happens is that the more time you spend harvesting coconuts, the harder it gets to reach them because you've used up all the easy to reach coconuts. So if you spend all day trying to harvest coconuts, you'll get all the easy ones first, and then it'll take you longer and longer to harvest successive coconuts because they're going to be harder and harder to get. So what that means is that if you give up 1 hour, so if you, let's say we start at this point over here where we have only harvested coconuts. If we were to give up 1 hour of harvesting coconuts and instead spent that hour fishing, we would only lose a little bit of coconuts because we will have given up that last hour that we spent getting the very highest coconuts. And in that 1 hour spent fishing, we're going to be able to harvest a ton of fish because that first hour spent fishing, we're going to be catching all the easy fish. Maybe they're ones that are close to shore. Maybe there's a special kind of fish on this island that when you call to them, they just jump out of the ocean and fall on the beach for you. But that initial hour that you trade giving up the 24th hour of harvesting coconuts to give the 1 hour of fishing, you're going to get a ton of more fish than you're giving up coconuts. Now, as you continue to give up hours, you're going to get less and less fish for the same reasons, because you're going to catch easy fish first, and the fish are going to get harder and harder to catch as the more time you spend on it, just like the coconuts were harder and harder to get. So that's why if I were here at this point, where I have relatively few coconuts and a lot of fish, if I give up 1 hour of harvesting coconuts, I barely get any extra fish because at that point fish are so hard to get. So this this type of nonlinear budget constraint represents diminishing returns. We're going to hear that phrase a lot. Diminishing. So in this case, we have diminishing returns to time spent harvesting. What that means is in the first hour we spend harvesting either coconuts or fish, it's a very productive hour. We catch a lot of fish or we harvest a lot of low-hanging coconuts. But then as we spend more time doing it, we end up harvesting fewer and fewer items per hour because they get harder and harder to obtain. The concept of diminishing returns is super important in economics. We're going to see it a lot. Okay, Notice this is in contrast to the linear case where the trade-off in between coconuts and fish was constant the whole time. All right. Okay, so here's an example for you to try. I'm not going to ask you to graph a nonlinear budget constraint in this video. We can talk about that more in class. But here's an example for you to do. Go ahead and pause it. I'm going to pause and write out the answer. So in just a second, the whole solution is going to appear on here. So pause it, read the example, and see if you can draw the budget constraint. Let's go ahead and put Pop-Tarts on the horizontal axis and Diet Coke on the vertical. Okay, catch in just a second. Okay, so here is the budget constraint for Diet Coke and Pop-Tarts. I got the intercept for Diet Coke by dividing $300 by $10 per case, and I got that I could afford 30 cases of Diet Coke if I only spent my money on Diet Coke. For Pop-Tarts, if I spend all $300 on Pop-Tarts, I can get 50 boxes. So that's this point down here. And then I just connect the dots. A really important thing that's going to come up later is the slope of a linear budget constraint. So I want you to take a second and figure out what the slope of this is. I'm going to put it on here, but I want you to do it on paper. So pause the video and try it, and then start it up again. Okay, so I did a bunch of calculations over here on the left to find the slope of this line. I labeled the 2 points here and here with their coordinates. I left it as 300 over 10 and 300 over 6 for a reason that you'll see in a second. So I went to calculate the slope. Change in y over change in x. Y1, if you want to call it that, is 300 over 10 minus 0. So y1, y2. Change in x, that makes this x1, and this one's x2. Standard slope, blah, blah, you get 300 over 10 divided by negative 300 over 6. Dividing fractions, multiply the reciprocal, the 300s cancel out, you get negative 6 over 10. Now, here's the reason that I didn't simplify anything. If you notice, 6 and 10 are the numbers from the original problem. 6 is the price of a box of Pop-Tarts, and 10 is the price of a case of Diet Coke. This actually isn't a coincidence. The slope of a budget constraint line is always going to be negative px, meaning whatever good is on the horizontal axis, over the price of the good that's on the vertical axis. We're going to end up using this a lot. So the slope of a linear budget constraint is always px over py. Obviously, it's a negative slope. But put that in your notes. We're going to be using that quite a bit. Okay, so these are the takeaways from this particular video about budget constraints. Budget constraints show all the possible combinations of goods that you can afford. So budget constraints are always about what you can get. Not necessarily what you want, but these are the things that you could potentially obtain. Budget constraints reflect a trade-off between how you use your resources to acquire goods. The slope of the budget constraint tells you the rate of that trade-off. This is what we just talked about on the last slide. The slope of a linear budget constraint is negative px over py. And then what we saw on a previous slide, the bundle of goods you end up choosing will always be on the budget constraint line. You will always spend your entire budget. You're not going to, in what we do this year, we're not going to be looking at, oh, if I have some money left over, maybe I'll save it or whatever. So you're always going to spend either all your time or all your money to produce goods. So you're always going to end up somewhere along the budget constraint line, not inside of it and not outside of it. And that's about it. Thanks.